We're going to look closer at the Pythagorean Theorem with this lesson. It's something we've been working with all year, but let's take a pause and just take a look at how, why, and what this Pythagorean Theorem is. So you know you have to have a right triangle. There's my right angle. And let's just put some labels here. Let's say this is A, and this is B, and this is C. And you know, of course, that I'm doing that because I want to have my hypotenuse right across from my right angle for C. Well, what does all this A squared plus B squared equals C squared even mean? Let me give you a look at it. A squared means that we're building a square with a side length of A. Of course, all the sides would be A since it's a square. And the area of that square is A times A. In other words, it's A squared. So we're talking about really the area of that square. The same could be said for B squared. It's a square with one side of B, another side of B, and the total area B squared. And of course, C squared, same story. So it would be a square with an area of C times C, C squared. So A squared plus B squared only equals C squared if you have a right triangle. And we could prove that if we could simply show that the area of my orange and the area of my blue squares are exactly the same as the area of my white square, my C squared. Now that's not going to happen. I'm going to try to fit this in, but I'm going to have to chop it up into pieces, of course. So here's the way I've chopped it up. And just as a demo, I want to show you how these pieces all fit inside of C squared. So let's take our B squared, these little pieces here, and let's just move them down into our C squared. This is a little bit like a puzzle, but they should fit pretty nicely, give or take. Bringing all these pieces down. Pretty much just fills in the corners, but what do you see there in the middle left over for me? Little adjustments needed here. Yeah, you get the idea. So yeah, my A squared can fit in there. So they fit right inside of there, and we've got the equal parts. A squared plus B squared equals C squared. So, of course, we need to know all this. So we're talking about a right triangle only. You need to make sure you have a right angle, and make sure your hypotenuse lands right across from that right angle. There's your hypotenuse. These guys are the legs over here, and there are A and B numbers. So we're going to take A, B, and C, and using C as the hypotenuse, squaring the two legs, adding them together, going to be the same thing as squaring the hypotenuse alone. Now, we've done these problems before, but with this lesson, we're going to have a focus on radical form. We've been practicing with the last couple of lessons, leaving them in the simplest radical form. Let's see how that works. First of all, I want to identify my hypotenuse as the 12. So let's set this up with 12 by itself, of course squared, and then we'll take x squared and 8 squared combined. Simplifying, I've got x squared plus 64 is equal to 144, and taking away 64 from both sides, that brings this down to just 80. And so I square root at the end of this. X is the square root of 80. Now do not get your calculator because we're not going into decimal. We're leaving it in exact, simplest radical form. So that's what we've been practicing. How do I get the square root of 80? Well, remember the little chart. We've got 1, 2, 3, 4, 5. Thinking of perfect squares. 1 squared, 2 squared, 3 squared, 9, 16, 25, and I'm looking for anything I could pull out of there. 49, 64, 81. So our square root of 80 is going to be in here. 64 doesn't go in. None of these go into it except for 16. 16 is my number I'm looking for. I'm going to change that to square root of 16 times by square root of, that's 5. 16 times 5 is 80. And then simplifying further, 4 square roots of 5. We're going to leave our answers just like that. Okay. How about this one? Now this one's a little different. You see square roots in my numbers. That can happen. Happens all the time if we're leaving in simplest radicals. All right, let's set it up. It looks like at this time x is our hypotenuse, so it's all alone. And let's just use these numbers. This is square root of 7 squared plus square root of 15, pulled from the triangle, squared from our formula. And these are actually a little easier than they look at first, but when you square and square root a number, that's an inverse thing. They're like, I should do my ninja yell, but I'm losing my voice. Those are canceling. That's what I'm trying to show you there. So we get to just bring out the 7. Same happens on this square, cancels the square root. We just get to bring out the 15. And joining those together for 22, still got x squared. Last step is the square root of 22 is our value for x. Can I simplify that? Does anything go into 22 from our number line? I don't think so. That's my final answer, square root of 22. Woohoo, word problem, we get to apply this. All right, let's read through it. To meet federal guidelines, a wheelchair ramp that is constructed to rise 1 foot off the ground must extend 12 feet along the ground. How long will the ramp be? So if you understand what that's saying, and you'll want to draw a picture, of course, we have a wheelchair ramp. We're trying to go up a ramp here, and the rise is 1 foot off the ground. So we want to have this vertical distance to be 1 foot. But it's got to, according to law, it has to extend 12 feet along the ground. So this direction is our 12 feet. And of course, we're going to have a right angle for the corner here. So how long does the ramp need to be? We want to get this slanted or this hypotenuse length. Let's put an x on there. And of course, this is a Pythagorean theorem again. All right, so setting it up with x as our hypotenuse, it's 1 squared, add 12 squared, and let it equal our x squared. And in calculating that as 1 plus 144, we have 145 total for x squared. So we're going to, of course, square root that. And that's our value for x. Now, we could leave that in simplest radical form, but I'm not going to for a couple of reasons. The first reason is this is my final answer, and it didn't ask me or tell me in the directions how to keep my answer. So I'm going to have to make a decision about what makes more sense. Does a radical answer make more sense here, or does a decimal approximation make more sense? Well, last time I checked, I haven't seen a ruler that has a radical in it. It doesn't measure by square root of 2 or square root of 3 inches. So a decimal really makes more sense if I'm going to physically build this ramp. So I'm going to grab my calculator, turn that into a decimal, just punch it in. Square root of 145, that's really close to 12, I'm not surprised, but it comes out a little bit bigger than 12, 12.04, and units, we're looking at feet here, so let's put a foot on there, and that's about how long we need that ramp to be. So sometimes it makes sense to put it into decimal, but if you're told to go into simplest radical form, that's the way you need to leave it. So that's Pythagorean theorem. It's a super famous theorem. You guys have done it. You've worked with it for a few years now even. It's really famous in movies. And I don't know if you've ever seen The Wizard of Oz. It's a pretty classic movie, but really famous movie, and they use the Pythagorean theorem in it. Unfortunately, they say it wrong. So I want to show you a clip. See if you can catch the mistake. I know Homer Simpson caught it. You'll see that too.
Why, anybody can have a brain. That's a very mediocre commodity. Every pusillanimous creature that crawls on the earth or slinks through slimy seas has a brain. Back where I come from, we have universities, seats of great learning, where men go to become great thinkers. And when they come out, they think deep thoughts, and with no more brains than you have. But they have one thing you haven't got, a diploma. Therefore, by virtue of the authority vested in me by the Universitatis Comitiatum e Pluribus Unum, I hereby confer upon you the honorary degree of Ph.D. Ph.D.? That's Doctor of Thinkology. Sum of the square roots of any two sides of an isosceles triangle is equal to the square root of the remaining side. Oh, John, I've got a brain.
Oh, hey, there's something you don't see in a toilet every day. Anybody lose their glasses? Last chance. Woohoo! The sum of the square roots of any two sides of an isosceles triangle is equal to the square root of the remaining side.
That's a right triangle, you idiot! Do!
Actually, Homer made a little mistake too. If you were paying attention, you would have seen it. Let me know in class. Let's do this. In class, you come and tell me what mistake Homer still made, and I'll give you a treat. All right, now, Pythagorean triples. I want to show you these because these are nice to know. And this little guy is here saying, be on the lookout for these. These are really just a shortcut, but they happen all the time. And so if you recognize a Pythagorean triple, you're going to have an easier time with lots of problems. It's a time saver. And what a Pythagorean triple is, well, let me show you a few of them. Here they are. Write these down. These are sets of numbers that work in the Pythagorean theorem. So let's just take this first one for example. If I have a triangle and the hypotenuse is the longest side, so let's note that this would be 5 here, and I've got 3 and 4. This is going to work in the Pythagorean theorem. In other words, 3 squared plus 4 squared is going to give you 5 squared every time. So let's see how that works. You got 9 and 16 right here. Combine them together is 25, which is indeed 5 squared. So it's pretty much just a way to memorize some answers for problems that come up a lot. So 3, 4, 5 will make a right triangle. 5, 12, 13 is another example. You can try those out. See if 5 squared plus 12 squared gives you 13 squared. Another one, 7, 24, 25. And 8, 15, 17. Now these are only 4 of them. There's actually, well, I think there's an infinite number, but they get into weird numbers that you'd never remember. So these are really the standard ones that you'll see more often than not. And as a little bonus, I just want to show you that they work extra. If you memorize, for example, 3, 4, 5, knowing that those make the sides of a right triangle, guess what else? If we times everything by 2, now it would become 6, 8, and 10. So I'm just doubling the 3 of them. 6, 8, and 10 also work in the Pythagorean theorem. You can check that. See if 6 squared plus 8 squared equals 10 squared. You'll find that it does. That's the same thing. So you can multiply these. You can multiply them all by 10. You might see 3 times 10 is 30. 4 times 10 is 40. 5 times 10 is 50. Those are going to make a right triangle. So the way these are used is if you look at a picture and you see maybe a 5 on a leg and a 12 on another leg, and you have to figure out what this hypotenuse is, you can generate the Pythagorean theorem with it. Or if you've memorized your triple, then you can just say, yep, that guy right there, he's 13. And so you can just kind of save a bunch of work. I love them. They're awesome, and they do come up often enough. So it's worth spending a little bit of time to memorize those numbers. All right, so when it comes to those Pythagorean triples, that's really the first thing I look for when I am looking at a Pythagorean theorem problem. Can I use a triple here? So what I'm checking to see is, with the 10 and the 12, what goes evenly into those? Well, 2 does. I can write this as 2 times 6, and I can write 10 as 2 times 5. So using those 6 and the 5 numbers, is there a triple with those? Where it's 5, something, and 6, and 6 is the hypotenuse. And you look at the list and you don't see any of those. So that means there's no triple I can use. It was worth a check because it comes up often enough that you'll love them when you see them. So this one we have to do from scratch. Let's work it through. Where's my hypotenuse? Always my first step. Right there is the 12. So this is going to say x squared and 10 squared. Add together makes 12 squared. When we go simplify that, x squared, this becomes 100. This is 144. Subtract the 100 over. X squared is 44. X is going to be the square root of 44. Now, we're going to simplify. Simplest radical form. What can we pull out of that? 44 is the same thing as 4 times 11. So let's take 4 as a perfect square times 11, both of those square rooted, and bring that down to just 2 square roots of 11. All right, we've got one last example now. I'm always going to make a check for those Pythagorean triples. They're a good shortcut. So let's look at this 14 and 48 and think about what you could maybe reduce them down to. Notice that they're both even, so 2 goes into both of those. In fact, 14 could be written as 2 times 7. And 48 could be written as 2 times 24. Now, look at those numbers, 7 and 24. Are they part of a triple? Is it a 7, 24? Look at your list. 25 is in that triple. 7, 24, 25 for the hypotenuse. So this hypotenuse, as a shortcut, I could just say is 25 from my 7, 24, 25 triple. But this triple's been doubled. Everything was times by 2. So I will times that by 2, and x is 50. And I didn't even have to do the Pythagorean theorem work. It's a neat trick. You can look for it. How about the try these? Maybe you'll find one in there. Give it a shot.